This is the second time to record the video. Today I present the paper named A Provision Model and its comparison with best effort for performance cost optimization in grades. And my name is Bai, and my research topic is try to use the data view system to do some data analysis in the cloud computing environment. So right now we are more focused on the cloud computing part, which has some advantages than the grades. But this paper is try to solve this kind of problem in grade, and this paper also focuses on the system perspective to do the resource provisioning part. First, I will introduce the outline of this presentation. First, I will introduce the characteristic of the grade and the resource allocation part in grades. Followed by the introduction part, I will introduce the provision model proposed in this paper, and then followed by I will introduce a simple application model used in the paper to compare the proposed method and the best effort method. As third part, I introduce the Pareto optimal size and give the definition of this size. Then a small example will introduce to have a deep understanding of the definition. The paper want to minimize the cost and the make a spend at the same time. So this problem can be treated as a multi-objective problem. It's very easy to know that this kind of problem can be solved with the multi-objective genetic algorithm. Then in order to compare the proposed method and the best effort method, a slot generating local scheduler is introduced to do the experiment for the best effort method. At last, I will conclude our show of the experiment results in this paper. As we all know that the grid have the structure that share the distribute infrastructure, and it means that the different kind of application in the grid can share the same server or the same computer resources, and also with this kind of character associated with the dynamic nature of the workload. And sometimes if one application is delayed, and the remaining part of all the application can be delayed. So based on the two characteristics of the grid and the agreement-based resource model is very necessary in the grid to make sure that a specific application can be run successfully in the grid. From the side of the resource provider, they have the two responsibilities. The first one is to optimize the utilization of the grid. And second one is they need to advise the available resources to users to make sure that they can submit their task or not. But from the side of the users, the user only want to have a good performance of the application run in grids. And in this paper, also the authors proposed a cost-based model where the providers advise resources available to the user committees with the optimize the application performance. Then a trace-based simulation is conducted to compare the proposed method and the best effort method. So let's move on to the computer resources provisioning model. And in the grid, the computing resources can be treated as different kind of resources slots. It means that you can cut the whole computing resources into different pieces, and each pieces can be treated as slot. So each slot is composed of 7 tuples. The first one is the start time of the slot, and the n means the number of processors in the slot, as d means the duration of the slot, and f is the extra cost for the slots. And b1 is the Boolean value, which indicates the slots can be indivisible or not. The e is very similar with the b, and e means that the slot can be extended or not. So if we want to provision the NK processors for duration d as at the start time as k given a slot, so we can have the actually we can have the 4 possibilities just based on the 2 indicators, the b and e. But the second case, which means that the slot cannot be divisible and can be extensible. It means that if we have this kind of location, so the cost will be too much than some other cases. So actually, when you have the 3 cases, the first one is a slot cannot be divisible and a slot cannot be extensible. Then we have the restriction that the slot can be treated as a slot. So we have the whole processors and the whole duration time and the whole ending time. And based on this logic, and we can have some other slot allocation. And then we can, based on this formula of the resource slots, and we extend and we can have all the resource slots between the time t0 and t0 and tn. So it means that we need to have the start time between t0 and tn. Let's move on to the application model. So it's very common to use the workflow as application model in the grids. So why do we need to use the workflow? And the workflow is composed of the different tasks and with some dependence. And we also have 2 assumptions for running workflow on the grids. The first one is that the task runtime is already known, and usually we can have the 2 strategies to get the runtime for the workflow. The first one is it can be estimated by using the component performance modeling, and the second one is it can be got by using the history information to infer the existing application. And second, another assumption is that the amount of data transferred between pair tasks are already known. So if all the tasks are run in one grid, it means that the data transfer time is 0. And if the tasks are run 2 different grids, and the data transfer time can be calculated with the bandwidth and latency. So the resource provision problem can be summarized as to find a subset of available resources to minimize the allocation cost and scheduling cost. So to make it consistent with other papers, and I will call the allocation cost to equal to the cost, and the scattering cost to equal to the mixed spin. Then we can have the cost were calculated by the number of the processors and the duration time and the unit price for the processor. And also the mixed spin can be calculated by dual manners between the lesser task finish time and the first task start time. What's a Pareto optimal site? So first of all, we have a resource plan A, and we also have another resource plan B. So if A and B can be composed a Pareto optimal site, and we can have these two plans cannot set to dominate. It means that A cannot dominate plan B. So let's move. So this problem can be transferred into what's a dominate problem. Then based on this example, and if the plan A is set to dominate plan B, and we can have the cases that the cost A equal to cost B and the mixed span A smaller than mixed span B, or cost A smaller than cost B and mixed span A equal to mixed span B, or cost A smaller than cost B and the mixed span A smaller than mixed span B. And based on this graph below, and we can see that the A3 dominates A5, and A2 dominates A4, A5, and A1 dominates A4, A5. So we can see that A1, A2, A3 can be composed of Pareto optimal sites. So the problem is in this paper is to minimize two problems. The first one is to minimize the cost, and another is to minimize the mixed span of the application. Here, this multi-objective problem can be transferred into a single optimization problem. The way by giving a weight of the different parts. And since we only have two functions to minimize, and we can add one parameter alpha, and another parameter is 1 minus alpha. And then we can transfer into the multi-objective problem into a single objective problem with a trade-off parameter alpha, and alpha can be changed between 0 and 1. So if we can find a minimum value with this function, and using the limited sorting space, and so the problem can be easy to find out. And also the provision candidates are selected in the Pareto optimal site. At the same time, one solution inside should satisfy this single optimization problem. Let's move on to the multiple objective genetic algorithm. So this algorithm is very similar with other genetic algorithms. So it uses a population of the certain number of solutions, and for the first thing is to have the initial population. How to get the initial population? So each population is expressed as a resource plan. The initial population is created by randomly picking a number between 0 and 2 power n minus 1, and then creates the resource plan. And a combined set is created by evaluating the cost and big spin efficiency function, and then the non-dominant member of this population are added to as a Pareto optimal set. Then a new population is created from the old one by using the genetic operator such as selection, crossover, and mutation. And then the new population should change the old population. So as we all know, if we want to select the Pareto optimal set, and we need to evaluate the cost and make spin at the same time. So the cost is calculated by this formula. And how to get the mixed spin of the scaling? The mixed spin is generated by any kind of scaling algorithm. So in this period, also use the Heft scaling algorithm. And as we all know that the Heft scaling algorithm is try to allocate different tasks to computer resources which have the earliest frame time. And the original Heft scaling algorithm is used into the processors. And right now the authors just change a little part to schedule a task in different kind of slots. So let's review the Heft scaling algorithm. The first one is to compute the rank of the odd application task. It from the exit task to the entry task. So the entry task should have the highest rank value. And this is a familiar how to calculate the rank of the workflow. Then we sort the task in list by the non-increasing rank values, and we select the first unscheduled task. And then for each slot in the available resources, and we need to compute the finish time for the specific task on this slot. If no slot can schedule this task, and it means that we cannot find a schedule method for this task. And then we schedule this task on the slot which lead to the earliest frame time. Then at last we need to update the slot schedule. Then we can return application task schedule on slot in this bin. So this is a delicate algorithm to schedule a task on a slot. And the first three is that it means that if we don't have enough processor for this specific task, and we return fail. And if the runtime of the task is the duration time of the slot is more than the runtime of the task, we also need to return fail. If the finish time is also smaller than the finish time, we also need to return fail. Then we need to sort the earliest available time for the processor in this slot. And then we need to calculate the actual start time for the task in this slot. which is the large one of the Easter earliest start time of this task and the available time for the processors. And then we need to extend its task into this slot, which has the earliest frame time. Then this algorithm will end. Error happen. So why the user selects the half the algorithm? And from the picture, we can see that the x-axis is the scaling algorithm names, and the y-axis is the non-dominated solutions. It means that the half can generate a lot of solutions than the three others. So the user will use the half algorithm to do a scaling part and use this kind of algorithm to get the mixed span value. And the left side application is generated by using a parameterized task graph generator. And this application consists of the 100 tasks with an average run time is 100 seconds. And then we use the multi-objective genetic algorithm on this application to record all the feasible solutions. And from the right side, we can see that we have more than 1,700 feasible solutions, but we only have more than 40 Pareto solutions. So in this case, and we can minimize the solution numbers at the most degree. Then we can use the existing 40 Pareto solutions to get the minimized value of the single optimization problem. But in order to compare the proposed method and the best effort method, and the author proposed the slot generating local scheduler. And this schedule can determine the free time period for processor from the current time and the future time period. So the user can use this schedule to reserve some resources. For example, in this example, the scheduler have already reserved 3 resources. It's reserved 1, reserved B, reserved 3, and then we can have this 6 free slots. And usually, in order to make sure that every professor can have at least 1 free period, and so the time period for this window should be larger than the last reserved end time. And for here, the slot 1 and the slot 2 and slot 3 is indivisible, and slot 4, slot 5, slot 6 can be extensible. So we can change the end time of these slots. Let's move on to the experiments. And in this picture, it shows the allocation cost and big span using best effort and provision approach for different trade-off factors. And for the SC cluster, the mix span of the provision approach is less than the best effort approach for the value of the trade-off factor alpha at the cost of increasing the local allocation cost. But however, for the CTC cluster, the provision mix span is lower than the best effort mix span for all the values of alpha. So why the CTS is better than the SC? It means maybe the reason is that the CTS has a lower workload on the cluster. So it means that the CTS have more available slots. And also the fact that mix span of the best effort is larger than the proposed method is because that the best effort method task should have some waiting time in the queue, and based on the current workload and all some other reasons. But for the proposed method, all the tasks can be located ahead of time, so they don't have any waiting times. I will mention that the allocation cost for the best effort is always the same. It's constant. Here is the allocation cost and the mix span using the best effort and provision approach for the varying task sets. It shows the effort of the task sets on the mix span and the allocation cost of best effort and the provision approach on the two clusters. A different task sets can be transferred into the needed processors for task. The proposed approach will use the trade-off value to represent the upper bound and lower bound value for the mix span and allocation cost. And for the two costs as the task size increased, the application performance in the proposed approach relative to the best method. That's it. Thank you.